All right, so definition of arc length. All right, so I'm going to draw an arbitrary curve. That is not what I had in mind. There's like a little bit of a lag here. This iPad doesn't know me yet. Yeah. Now I'm going to bring in the graph a little bit and draw a few little line segments here. I'll go from here to here. All right. So this goes right back to limit, the concept of a limit, but also the limit definition of a derivative way back in the beginning of Calc 1. All right, what we're looking at here is the slope, a slope of a line connecting two points along the curve. All right, so if I call this A and I call this B, if I wanted the slope, this would be f of B minus f of A over B minus A, also known as the average rate of change. All right, so that's old news, all the way back to algebra. Find the change of y over change in x. That's all an average rate of change is. All right, we just make it look fancier than it really is. All right, but then what happened in Calc 1 is, man, the points got closer and closer, or the second point anyway, got closer and closer to the first point. And eventually what you got was a tangent line. Let me make that thicker. Do it that way. So it ended up looking something like this. All right, so this is a tangent line. Which we define in terms of the slope anyway. The slope would be f prime at A. All right, so whatever the A value is, we would find the derivative, plug that A value in, and then just call it a day. And that would give us a slope at that particular tangent line. So that's an instantaneous rate of change. Instantaneous rate of change. All right, so that's a little bit of background. At no point have we found a length, though. All right, what we're going to do now is we're going to kind of take it in a little bit of a different direction. I'm going to draw the same arbitrary curve. Even if I said I was going to draw a different arbitrary curve, it would always end up being the same one. That's just how I do things. Creature of habit. So what I want to do now is find the length over A to B. So I want the distance from A to B. Now, you can see the formula is below, so you kind of know where this is going. It's going to involve an integral. But what's going to happen is something that might end up being somewhat, I don't want to call it surprising, because I think that's a little too dramatic. But what we're going to do is find little instantaneous distances along the curve and then integrate them all together. All right? So what I'm going to do is I can't find the distance from A to B directly. I mean, if I wanted to, I could connect A to B with a line segment and then measure that. And I get like a ballpark estimate. It would be an underestimate, but I'd get something in the neighborhood of the right answer. But if you were to think about this, if I were to give, and sometimes elementary school students have a better understanding of this stuff than we do. If I told a third grader to find the distance from A to B, what they might actually start doing with a ruler is working their way around the curve. And you say, well, that's absurd. I don't want to do it that way, but that's actually the right way to do it. So they take the ruler, measure a little tiny line segment, take note of what it is, then get the next little tiny line segment, then get the next one, and then kind of inch their way around. Kind of like you would if you were to estimate the distance on a map, like back when you actually had to use maps instead of like Waze and Google. My wife and I have constantly, we argue. The minute the Waze app fails, she's like, see, I told you the Google Maps are better. Like, I don't know why I use this stupid thing. From my perspective, it's police reported half a mile up the road. You know, that's the only reason I have mine set to like British English. So it sounds fancier. I like it that way. But yeah, that's all I have it on for. I'll take the crappy directions as long as you tell me there's a cop up the road. All right, you know, I never have an intention of speeding. I just always end up doing it. So it's nice to have a little bit of a heads up that it's coming. Now the problem is, the only way people can get notified that there's a cop up the road is if somebody has already seen the cop. Now, if that's the case, they may have found out the hard way, in which case the cop is not in that position anymore. But I just like the constant reminder, hey, you're probably going too fast. Because you know it doesn't work? When that little speed sign comes up on the app that says 55 miles an hour, I'm like, yeah, cool. Thanks for the heads up. The speed limit is 55. And then I'll look over, oh, that's why you put that up there. Because I am not going 55 miles an hour. You know, but it doesn't help. It's the constant verbal reminder. I like it. Right? But we don't use paper maps anymore. And because of that, my little analogy of like finding distances on the road, that doesn't really always land. But maybe you did it in elementary school, I don't know. But that's actually what we're going to do. So I'm going to take a little smidge of a distance, like right here. I want to at least get the scale somewhat reasonable. And figure out what that is. Which is kind of weird, all right? But what we're going to do is make an assumption here, all right? We're going to assume that this is an instantaneous rate of change. So we're going to call this an instantaneous distance. Which kind of sounds like an oxymoron, I guess. It's like, how can you have traveled any kind of distance instantaneously? It's just basically saying, you know, that distance from point A to point B, it has some value, but as that value approaches zero, the slope, change in y over change in x, approaches the derivative at that point. All right? So this point here has a derivative, or at least this little line segment has a derivative, f prime of x over 1, change in y over change in x. I'm going to keep it in general terms. I think it makes sense to do it that way. All right, so some x value, x corresponding to a. All right, and that's because slope is equal to change in y over change in x. If I tell you that the slope is equal to f prime of x, I could make a fraction out of this. F prime of x over 1 would correspond to change in y over change in x. So I'm making my vertical change f prime of x, my horizontal change 1. All right? So now when I zoom out, this is going to be obnoxiously small, but it is what it is. I haven't quite figured that part of this thing out yet. All right, but what I'm going to do is I'm going to draw the triangle at a more reasonable scale here. So f prime of x and 1. All right, base and height. Now if I want the hypotenuse, I just use Pythagorean theorem. All right. So the sum of the squares added together, well, that would be the sum. The squared values added together under a root. So the square root of 1 plus f prime of x squared. I gotta clean that up. I'm sorry. That looks terrible. All right, so that's actually what that instantaneous distance is going to be. Each one of these tiny little distances, as they work their way around, is going to be equivalent to the square root of 1 plus f prime of x squared. All right, so if I collect every possible little tiny distance, so if I get this one, followed by that one, oh, that's poor quality, followed by this one, followed by this one, followed by this one. You know, I'm drawing the line segments too big, but the idea is that you'd have like all these little tiny distances all along the interval that you're looking for. Each one of those teensy tiny smidges of distances would be expressed by the square root of 1 plus f prime of x squared. So the way we collect all of them over the interval is by integrating. Right? It's the same idea as cross sections when we're finding volumes using cross sections. We find an expression that represents any cross section, and then we integrate them all together so that we find the sum total of all of them. All right, so if I take on the interval of a to b, one plus f prime of x squared dx, all right, the dx allows for any possible change in x. All right, so we're multiplying this by all the different changes in x, and that gets us from the beginning to the end. What we have is an expression that represents arc length. All right, or I mean, we call it arc length. I think it's a misnomer because arc length typically corresponds with arcs in a circle. All right, but technically, and this is kind of a little bit beyond, every little segment on a curve is an arc length of a circle. It's just they're not all the same circle. All right, so that's more Calc 3 when you start getting into the concept of curvature. But I'll just show you real quick. I won't do any of the math. I'll just give you a little bit of a sense. So arbitrary curve on A to B. Let's say I just wanted this segment here. That segment is the arc of some circle that has its own center and radius. If I add another circle, another arc, I mean, let's say this one is kind of bowed upward a little bit. Let's say I only wanted this one. Actually, the flatter it is, the crazier it becomes, because the flatter it is, the larger the circle might be. All right, so this might be some astronomically large circle, but I'm just going to kind of fake it a little bit. But the only purpose behind this whole circle is to come up with this little sliver of arc. All right, that little sector gives us this little arc length. All right. So when we talk about the concept of arc length, we're actually talking about it as part of the circumference of a circle. It's just we tend not to think of it that way, like when we're actually working it through mathematically. But it's kind of interesting. All right, there's a whole section of Calc 3 that deals with all that. So more Calc 3 to get excited for. All right, so your two formulas, S equals what we just came up with. S stands for arc length, because why not? Well, use A for so many other things. That's really what they get at. S equals r theta. when you're dealing with circles. So they designate it in geometry that S represents the arc length. So they're just kind of carrying that over from there. The other formula is just when you're dealing with an equation in terms of y. The process is not terrible. So it's actually something to kind of look forward to, because there's no trick to it. It's just follow the formula. So the first thing I would need is f prime of x. So if we assume that f of x is equal to the natural log of the cosine of x, then f prime of x, natural log of cosine, 1 over cosine times negative sine, which equates to a negative tangent when you clean it up. It's not something that you actually need to clean up too much. You can write it as negative sine over cosine, but if you want to type this in your calculator, obviously you want to have the cleaner expression to put in there. The cleaner the expression, the better. All right, so if I want the length of the arc on that interval, the expression I'm coming up with would just simply be 0 to pi over 4, 1 plus negative tan x squared dx. Now this would become a calculator problem because we actually haven't gotten to little shortcuts related to finding trig integrals and stuff like that. That's more so later on in this unit. So we're still at the plugging and chugging portion of things. Calculator. So the only thing you have to remember is put your calculator in radian mode. So math 9, pi over 4. So we're looking at about 0.88-ish, approximately. Just double check. All right. So it's a small interval going from 0 to pi over 4, so we're not expecting some monstrously large number. All right. Number 2 is along the same lines. Find the length of the arc of the graph on the interval given. So first step again, find the derivative, but it makes sense to write the function in more convenient terms. So 1 over 6 x cubed plus 1/2 x to the negative first. That's what I would do first, because I want to get it in something that's power rule ready. Because remember, we're taking the derivative. Right? Whenever you're taking the derivative, or even antiderivative, the idea is to come up with the most convenient form of the expression. All right? So f prime would be 3/6, so 1/2 x squared minus 1/2 x to the negative second. All right, so now it's just a matter of popping it into the formula. So going from 1/2 to 2, square root of 1 plus the 1/2 x squared minus 1/2 x to the negative second, the whole quantity squared dx. All right, so kind of a pain to put in your calculator, but not nearly the kind of a pain that it would be if you had to do it by hand. So the definite integral rules are still in effect, and that means if you're presented with a definite integral, you can go right to the calculator. It's the indefinite integrals you may have to do by hand. And in this unit, you'll definitely have to do it by hand, because for some of them, there's no way around it. Yeah, so just pop it in, double check. Here's hoping. I kind of half double checked, so I single checked. Bless you. So 2.0625 math frac, or 33/16 if you want to put it in exact form. All right, so nothing too crazy when it comes down to it. So the area of a surface of revolution, so it's also known as surface area. Now, from this, you could actually get some of your geometry rules, like surface area of a sphere or something along those lines, but only things that would be considered smooth curves, all right? Because if it's not continuous and differentiable for all values of x or y, then this technique would fail, all right? But you'll notice in each case that you're dealing with essentially the arc length formula. Right? It's got this extra business going on. So our only job in this little space above is to figure out what that little extra business is. All right, so I'm going to draw an arbitrary curve. A little smoother at the end. I'm going to give it a set of axes. And I'll say that I'm spinning it around the horizontal axis. All right. Now, we kind of have a sense based off of the last unit, what would happen if I spun this around and I was looking for volume. You talk about this method or cylindrical shells method, right? But now what we're looking for is the surface area. So I'm looking for a measure that represents the value of the outermost surface, not all the stuff that's contained within. All right, but you still have to spin it. So do that. I'm going to use the disk approach. So I'm going to have some distance, and that. No, I'm just going to go. You can do it for a bunch of different places if you want, but one is enough. All right, but what I'm going to do is I'm going to give it a little bit of thickness. All right, so I'm going to bring it in a little bit, and along the surface, I'm going to draw a little line segment here. I got to change the thickness. I'll bring it out. All right. So what I'm doing is I'm taking a little teensy tiny section of the distance along the curve, and I'm spinning just that. Not all the stuff in between, just that little teensy tiny distance, which is going to create a little strip of the surface. All right. So it'll give you a little tiny little smidge of the surface as it gets spun around. Right, in 360 degrees. So it'll give you all the way around, but it's only going to give you that one strip. Now, that little distance here along the curve, that's an arc length that we call S. All right. So what I want to do is account for the not the area, but the circumference as I work my way around, right? So I have that one dimension, that gives me the thickness, but I want to take that and go all the way around the circle. So I want to go all the way around the circumference. So if I take just that one ring, so let me just call it the inner ring. So just this one guy here, I should do that in a different color. Let's go purple for those keeping score at home. All right, circumference C equals 2 pi r. All right. So if I want to get the surface area of the single strip, surface area of the strip, I'm going to take the 2 pi r and multiply that by s. And we discovered on the previous page that s, so 2 pi r, s is the same as the square root of 1 plus f prime of x quantity squared. Well, assuming it is a quantity. All right, so we have 2 pi r multiplied by the arc length. Thank you. I kept see the s and I just can't stop myself. All right, so then the only question would become, well, how do I come up with that r value? Well, if I look at my diagram here, this distance here is r. All right, so r is the distance from your axis of revolution to the outermost portion of the surface. All right, so r, again, is the distance from axis of revolution. And so that's really where our formulas come from, okay? But it depends. You know, I wrote f prime of x. Really, I guess I could have just written f prime because it could go with respect to x or y. But I drew mine so that it was going around a horizontal axis of revolution. So whatever I defined r as, it was going to be in terms of x because the thickness r is going to be dx. All right, so integrating over the interval of a to b, if I drew in a to b, I would have all of these little, they wouldn't really be slices. I mean, there would be essentially slices, but we only care about the outer edges of it, right? So I wouldn't care about the meat inside of it. That would all get pulled out, all right? So all those little strips of surface integrated over the interval would give us the surface area in its entirety, right? So, if you're spinning around a horizontal axis of revolution, it's tailor-made for a function that's in terms of x. All right. So, and if you're going around a vertical one, you do it in terms of y generally. All right. There's exceptions to that, but that's the general rule of thumb. All right. So, the idea here is that if you have a sense in your mind that you're looking for circumference multiplied by arc length, then you have your surface area. All right. But you can see what I was talking about before, where I was saying that it gets confused with cylindrical shells pretty easily, because cylindrical shell starts off with a 2 pi, you have your interval of a to b, and then two things being multiplied with a dx or dy. All right, it's very easy to get the two confused, so it's kind of working out that it's in the second unit. So it's a happy mistake, I guess. All right, so f of x is equal to x cubed on the interval of 0 to 1. So I'm going to find f prime of x is equal to 3x squared. So that's part of my equation. I'm going to draw a little sketch of x cubed. We only care about it over the interval of 0 to 1. So it's going to look something like this. Here's 0, and here's 1. It's getting spun around the x-axis. So you just want to think about how your radius would be oriented. All right. So it's oriented vertically. So this would be a dx. So so 2 pi on the interval of 0 to 1, we need a measure that represents the radius. And then we need the square root, bless you, of 1 plus the derivative, 3x squared. All right, now the one thing you have to consider is how you get from the axis of revolution to the curve in question. All right, it's a vertical displacement. All right, what you're doing is you're going up y units. All right, because the distance from the x-axis to any point in space is defined as y. All right, so this would be y, but you have a disagreement with the argument here of x. All right, the integral is in terms of x, and so if you have a y in there, that's no good unless you're in Calc 3. Not yet, you'll get there. So if this is going to be y, you would want to be thinking about, okay, well, what's y equivalent to in this situation? Well, if it's on this curve, and it is, then it follows y equals x cubed. So I can throw in an x cubed here, and then run that through the calculator, and be done with it. Double checking. So we're looking at about 3.56-ish. So approximately 3.56. So number 2, find the surface area formed by revolving the graph of on 0 to 2, root 2, about the y-axis. All right, so y equals x squared. Not a crazy difficult thing to graph, even on a rooted interval. 0, 0, root 2 is right here. Root 2 squared is a positive 2, so make that a 2. So we're talking, and we're spinning it around the y-axis. All right. Now, if I'm spinning it around the y-axis, that's creating a horizontal radius. So that's a dy. All right, my distance is y. All right, but that's telling me that I want to change some things up. Now, you can actually work with this in terms of x. It's just for consistency between this and volumes of revolution, you kind of want to change things up a little bit. All right, so the first thing I would do is change my function. So y equals x squared. Let's make that x equals the square root of y. All right, we can go with only the positive because we're living on the right-hand side of the y-axis. All right. So then I need my derivative. So this is really, you could write this as f of y is equal to y to the 1/2, which means that f prime of y is going to be 1/2 y to the negative 1/2. My bounds, this was on the interval of 0 to root 2. This one is now on the interval of 0 to 2. All right. So I plug in my x bounds to my function and get the corresponding y bounds. All right, so not much really of an adjustment. All right, so once you do that, you're ready to rock and roll because it's 2 pi. We have our interval 0 to 2. The radius, which is some y distance, and this is the nice aspect of this, I'll get to that in a sec, multiplied by the square root of 1 plus 1/2 y to the negative 1/2 quantity squared dy. All right. Now, on the previous one, what I had to do was, because I needed to plug in, oh, sorry, what did I write here? Oh, jeez Louise. I wrote it here. I don't know why I did. That's an x. What I was going to do is say how great it was that we didn't even have to like worry about figuring out what y was, because this is in terms of y. We just put the y. But that's supposed to be an x. So it's one of my prouder moments, I guess. All right, so x is equal to the square root of y. Pop that right in. And then just check, make sure everything's in terms of y. It is. We're in good shape. So 2 pi math 9 on the interval of 0 to 2 square root. Now you can use y's, but I just default to x's. It doesn't end up mattering. Just the one thing I'll caution you about is, let me just double check, make sure. Yeah. We're looking at about 13.61 approximately. I noticed this when I was grading the tests. A couple of folks, you know, you have a function that on paper is supposed to be in terms of y, but in your calculator you put it in terms of x just for convenience. But what was happening was some folks they had the right function, but everywhere there was a y, there was supposed to be an x. So what I think was happening was those individuals were like just writing down what they were typing into their calculator. And they're like, well, this is what I put in my calculator. Meanwhile, they had all the background information correct to get the right answer. They just zigged when they should have zagged. So you just gotta be careful about stuff like that. But then again, I mean, I wrote a y here when I was supposed to write an x, so it could happen to anyone. So I'll just create a little side example here. Number 3, if somebody wants a typo bonus point. Just want to make sure I get it right. Yeah. All right, so surface area of y equals the square root of 1 minus x squared on the interval of -1 to 1. Yeah, -1 to 1. Question?
On the last question, you got your new intervals, but plugging in the old intervals into the new function?
You got it. Yeah, because those were x intervals, so we needed them to go for y. So whenever you have a relation between x and y, you could always just do direct substitution. All right, so it's a spontaneous question that I created, but it's for a purpose. We'll see if we get what I'm hoping to get. Find out in a minute. So press double check. Yeah, it should work. Yeah, that's what I want. All right, so we have a graph, and you can just snag the graph from the calculator, but it goes from -1 to 1. And you're looking at a semicircle. So it's going up to 1. All right, it's getting spun around the axis. I mean, I'm not even going to bother trying to draw it, but if you take a semicircle and spin it around the axis, it should create a sphere. Alright, so a sphere with radius of 1. Surface area of a sphere, there's a formula for that. So what we're going to try to do is come up with that formula. Alright, so we have a radius that has a thickness dx. We're spinning it around the x-axis. Alright, so there's no disagreement between the way the function is given to us and what we're looking for. So that's good news. Okay, so what I need to do is set up my equation. S, well, A area, but I'll just go with the expression. 2 pi on the interval of -1 to 1. Radius, which is y, multiplied by the arc length part of it. So I need the derivative of this, which involves a teensy little bit of chain rule. All right, so just off on the side here, I'm going to do y equals 1 minus x squared to the 1/2 power, in which case we'll get y prime 1/2 times 1 minus x squared to the -1/2 times -2x. I'm just going to clean that up a little bit just for the sake of writing something nicer into the model. So we're looking at -x over the square root of 1 minus x squared. All right, so that's my derivative. So that's going to get chucked in my arc length formula. Now, the y value, I just cut to the chase. Y is equal to the square root of 1 minus x squared. So I could just pop that right in. So then multiply by the square root of 1 plus -x over the square root of 1 minus x squared squared, all dx. All right. So, I mean, if you know what the formula is for surface area of a sphere, you should know that this will clean up, or it should clean up kind of nicely. Right? So, and in fact, it'll clean up beautifully. It just doesn't seem like it at first glance. But again, I mean, I'm not going to renege on my promises. It's a definite integral, so you don't have to do it by hand. Although, you may want to simplify it a little bit just for the sake of making it easier to put in your calculator, but even that's not a requirement. All right, so 1 plus quantity squared. Type that in right. I think so. We'll see in a sec. All right, so you get this decimal. When you do, after all of that, it's a big mess. But you get this decimal, 12.56637061. All right. Well, I wouldn't, only because this is some multiple of pi, because there's a pi built in as a constant multiple. So if you actually divide this number by pi, you actually get 4. So this is the equivalent of 4 pi. So instead of having to worry about rounding and doing it the right way, if you account for the fact that it's a multiple of pi, you could get a cleaner answer, right? And a way to deal with this without actually having to worry about dividing by pi would be to say, well, let me leave the pi out, run the calculation without the pi in it, knowing that I could just slap the pi on later on. If you ran this without the pi, you should have gotten a 4, knowing that you could just pop the pi right onto the 4 afterwards. All right, so you look at that and say, okay, cool, like fabulous, I'm glad you did this problem. So like, what's the benefit? All right, so area, surface area of a sphere. The rule is area is equal to four pi r squared. All right, radius equal to 1. Therefore, area is equal to 4 pi. All right, so if you knew that you were on the lookout for a sphere, just based off of the information given to you, then you would have an idea what the answer ought to be going in. Now, I've mentioned this a few times, but it's not like the kind of thing that I repeat over and over again. And that is, if you're solving a problem and you find that you're not doing calculus in the solution of that problem, you're probably doing it the wrong way. But there are little exceptions to that. Sometimes I like to throw a problem on a test where I know you could do it a different way and just word the instructions in a way that leaves it open-ended enough for you to look for a shortcut, right? And sometimes I just kind of steer you right in that direction. I'll say, find the surface area of this, blah, 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 using either an integration approach or a geometric approach, in which case everything's fair game. The only thing that I would need you to show is a diagram, a brief explanation of how you know it's going to be a sphere, and then the calculations to get the surface area. All right, so I'm not going to promise that that's going to be a question on the next test, but it's my kind of question. All right, so I mean, when we were going over the derivation of the position function, I mean, I don't know how else I could have clued you in that was going to be on the test, other than to flat out say it's going to be on the test. But I mean, for those of you who are kind of aware of that sort of thing, you knew it was coming, right? But I cut it short. I was nice. I was a little stop at velocity. It was like a 2.5-step problem, all right? So that was kind of a nice little something for you if you knew to expect it. Honestly, I will say that in most cases, people look for the proof and then they say, omit, I'm not even going to try it. On this test, more than any other test, I had people at least attempting that last question. Mostly to get out of having to do the cross-section question. I know.